Hi everyone. Welcome to Dr. Engineering's FPGA design tutorial series. I'm Dr. Engineering.
In this series, we'll be learning how to master FPGA design through hands-on practice, not through boring theory. Our motto is learn from practice, meaning you won't get bogged down in tedious concepts but will instead learn by applying what you know step by step. If you find this interesting, make sure to subscribe to my channel so you don't miss any future videos. And if you have any questions, feel free to leave a comment, and I'll try to answer them as soon as possible.
Ready to dive in? Let's get started. And today we're moving on to something super exciting. The full adder.
In the last lesson, we covered the basics of the half adder, and today we'll build on that by learning about the full adder.
Today's lesson will introduce what is full adder, how it works, as well as its applications. Same as previous lesson, we will learn how to implement and simulate it in Vivado using VHDL. So let's jump right in. First, let's start with an overview of what a full adder is and how it works. A full adder is a fundamental building block in digital circuits.
That adds 3 binary bits, 2 input bits, and a carry bit from a previous addition. Unlike the half adder, which can only add 2 bits, the full adder accounts for carry in and carry out, making it a key element for performing multi-bit binary addition. A full adder takes 3 inputs, A, and Cin, the carry input from the previous addition, and it gives 2 outputs, sum and cout, the carry output for the next stage. The basic formulas for the outputs are derived from the truth table of the full adder. As you can see, the full adder sums these 3 inputs and generates a sum bit and a carryout bit. The sum is computed using an XOR operation, while the carryout is generated using AND or gates.
Let's break down the full adder's schematic step by step, making it easier to design and analyze later on.
In this schematic, we've broken these equations into smaller, manageable logic gates to show how the outputs are constructed.
First, we calculate the intermediate signal W_1, which is the XOR of A and B.
This is crucial, because it forms part of both the sum and cout equations.
As mentioned in the half adder lesson, we use prefix W_ to indicate it's a wire-type signal.
And it connects parts of the circuit. Next, we calculate 2 more intermediate signals, W_2 and W_3, which help determine the carryout, cout. W_2 is the in of W_1 and Cin, helping to track whether both Cin and the XOR of A and B are high. W_3 is the N of A and B, ensuring that the carry happens when both inputs A and B are high. Now, let's calculate the outputs. The sum is calculated by XOR W_1 with Cin, as per the full adder equation. The cout is obtained by OR W_2 and W_3, covering all cases where a carry is needed. In summary, we've taken the full adder formula, split it into logical parts, and built it with simple logic gates, XORs, ANDs, and ORs. This not only makes the circuit easier to implement but also easier to test and troubleshoot in the simulation phase. Now, let's talk about the key advantages of the full adder over the half adder. The full adder offers some crucial improvements that make it an essential part of digital circuit design. Here are the main points. 1. Supports carry in. Unlike the half adder, the full adder can add a carry input from the previous stage, allowing it to perform multi-bit binary addition. 2. Lower power consumption. Surprisingly, the full adder consumes less power than the half adder, making it more efficient in energy-sensitive applications. 3. Easily convertible to half subtractor. With just the addition of a NOT gate, the full adder can also be turned into a half subtractor, giving it more flexibility in digital circuits. For higher output capability, the full adder generates a higher quality output compared to the half adder, making it more suitable for complex operations. 5. Essential for critical circuits. Full adders are a key component in complex digital circuits, such as multiplexers, where accurate binary addition is crucial. 6. Faster operation. Full adders are designed to work at higher speeds, which is critical in applications like processors, where fast computation is necessary. Now, let's dive into the applications of the full adder. Full adders play a crucial role in many important digital systems. 1. Used in ALUs, arithmetic logic units. Full adders are a core part of the ALUs found in CPU architectures.
They perform binary addition, which is a fundamental operation for many arithmetic functions. 2. Calculator circuits. Full adders are also used in calculators to carry out addition operations on binary numbers, which is the basis of how calculators process information. 3. Binary multiplication. Full adders help in multiplying binary numbers by adding partial products, making them essential for binary multiplication processes. For a key component in multiplexers, full adders are used in designing multiplexers, which are critical in routing data through multiple paths in a circuit. 5. Memory address generation. Full adders assist in generating memory addresses in digital systems, ensuring accurate data storage and retrieval. 6. Program counters. In CPUs, full adders are used to generate program counter values, which are crucial for the sequential execution of instructions. 7. GPUs. Graphical processing units. Full adders are also found in GPUs, helping to process multiple parallel operations for rendering graphics and accelerating computing tasks. That's all the introduction of the full adder. Let's move to the implementation part and build a full adder together. Just like in the previous lesson, we'll start by opening Vivado and click on Create Project to create a new project. The process is the same as in the last lesson on the half adder. This time, we'll name the project full_adder, and the following steps are exactly the same as before. If this is your first time watching my tutorials and you're unfamiliar with the software, I recommend checking out the half adder lesson in my tutorial series, where I provide a detailed step-by-step guide on how to design and simulate using Vivado. Once the project is created, select Add Source. Here, we'll create the design file for the circuit. Defining the inputs as A, B, and C in, and we'll add the prefix I underscore to mark them as input signals. Similarly, we'll define the outputs S and C out, adding the O underscore prefix to mark them as output signals. Once that's done, open the generated file. Let's add a comment to separate the inputs from the outputs, aligning the signals to make them easier to observe. With that, the entity is complete. Now, let's review the content from the last lesson and briefly go over the concepts of entity and architecture. An entity is like a black box. It defines the inputs and outputs of a circuit but doesn't tell us what happens inside. The architecture describes the internal workings of this black box. If we compare VHDL to programming in C, the entity in VHDL can be seen as declaring a function, while the architecture describes the function's behavior. The port in VHDL is like the pointers passed into a C function. I use this comparison to make it easier to understand, but keep in mind that VHDL describes hardware, whereas C describes software. We're learning VHDL, not VSDL. Next, we'll write the architecture, which describes the internal structure of the circuit. Based on the schematic analysis, we declare intermediate variables, W_1, W_2, W_3.
Then, in the begin block, we define the behavior of each variable. You could also write out the final equation to directly describe the relationship between the inputs and outputs, but if the circuit doesn't behave as expected during simulation, debugging becomes challenging.
A single long equation makes it harder to track down the issue.
When we load the circuit onto an FPGA, all ports are connected based on our design as soon as power is supplied. So, both approaches, using intermediate variables or long equations, will have the same efficiency and behavior in real hardware. To keep things clear and manageable, we'll stick with the version using intermediate variables.
At this point, the circuit design is complete. Now, we'll move on to creating the test bench.
Click Save and go back to the Sources panel to add a new source.
Like in the previous lesson, we'll create a test bench file with the suffix tb. The test bench has no external interfaces, so we can just click Finish. Open the test bench file.
Since there are no external interfaces, we'll leave the entity as is and focus on designing the architecture for the test bench.
Let's quickly review the content from the previous lesson. The purpose of a test bench is to create a signal processing mechanism to test the circuit we've designed.
This signal processing essentially forms the architecture of the test bench, and the signals we use must correspond to the inputs and outputs of the circuit.
We'll start by defining the signals needed for the test bench architecture. As before, we'll use R_4 register type signals and W_4 wire type signals. Even though VHDL doesn't differentiate between registers and wires, it only uses signal. We use this definition from Verilog to clarify the function of each signal. This helps improve design efficiency, especially in complex circuits, and reduces the risk of errors. Plus, if you later transition to or work with Verilog, this naming approach will ease the shift from VHDL to Verilog. Now, let's move on to declaring the UUT, unit under test. To help clarify what UUT means, let me give you an example. Imagine you've designed a circuit, similar to releasing a new smartphone model. The company will produce many units of this phone, all identical because they come from the same design and factory. When someone buys this phone, it's like they've declared a UUT. This phone has all the features we designed and manufactured. When the user plays music, watches videos, or plays games, they're essentially testing out all the functions of the phone, just like we do with our test bench when we test the circuit. I hope this analogy makes it easier to understand the relationship between circuit design and simulation. Now, back to the test bench design.
A few moments later.
After declaring the UUT, we need to generate the input signals for testing. Since today we're working with 3 different signals and a wide range of combinations, manually defining each input case like we did in the last lesson would be cumbersome. Instead, we'll use a simpler method to generate these signals. Based on the truth table, we can draw the waveforms for the 3 input signals. Looking at the waveforms, we notice that the periods of A, B, and C double progressively. So, we can use clock-like processes to define each input signal in a process block. Below the signal declarations, we add a constant declaration for the clock period. We define it as clock_period, and specify it as a time type, giving it a value of 5 nanoseconds. Let's start with signal A. According to the waveform, we initialize A to 0. Wait for 1 clock period. Then set A to 1, high, and wait for another clock period. This process will repeat indefinitely. In VHDL, the process block loops continuously, so A is now set. Next, we copy A's process and rename it for signal B based on the waveform. We want B to remain low for 2 clock periods before toggling. So, we simply double the clock period for B. Now B is set. Following the same logic, we set up C in. Its period is twice that of B in, so we quadruple the clock period for C in. These 3 processes will execute in parallel. In FPGA, all processes run simultaneously once power is supplied, unlike software programming languages like C, where each statement runs sequentially. In VHDL, all statements start execution simultaneously. Think of it like a power strip. When you turn it on, all connected devices receive power at the same time, but some devices power on faster than others. This is similar to how the wait statements introduce delays, but the power is supplied all at once. With that, the test bench is complete. Like before, let's run the simulation. First, go to the settings, set the simulation time to 50 nanoseconds, which is enough to observe all the changes in the truth table. Then click Run. For better viewing, click Zoom Fit. Now, compare the input and output waveforms with the truth table. Everything matches perfectly, which means the design is complete. To verify the long equations used in the circuit design, we can go back, comment out the intermediate variables using Ctrl+//, and run the simulation again using only the long equations. You'll see that the waveforms remain the same. And with that, we've finished the design. That's it for today's lesson. We've introduced the full adder, implemented it in VHDL, and simulated it using a test bench in Vivado. The full adder is a key component in many digital systems, so mastering it is crucial if you're working with FPGAs. If you found this lesson helpful, make sure to give it a thumbs up and subscribe to the channel for more VHDL tutorials. And if you have any questions or suggestions, feel free to leave a comment below. Thanks for watching, and I'll see you in the next video.